let's take a brief look at pairs and lists, and what they actually look like once we've expanded them. So here is cons of A applied to cons of B of C. This may seem like a non-obvious order, but remember, applications go left to right, so we explicitly parenthesized cons B, C to make sure that it was cons of A, so the head is A, and the tail is a cons. The tail is the cons of B and C. So this is cons of B and C, and this is cons of A and the result of cons in B and C. Now, in AOR, we will expand the cons first. So cons expands to lambda h dot lambda t dot lambda s dot sht. So S is our selector, and it lets us choose whether we want the head or the tail, very, very similarly to true and false from before. A is just a free variable. I'm just trying to make a list ABC. So when we substitute A in for H, since A is the head of this list, we simply get H here, substituted for A. Now we have lambda t dot lambda s dot SAT. A still being a free variable. There's nothing left to expand on the left, so we look for the innermost leftmost on the right. Cons of B will go through the exact same process. Cons expands, then the free variable B is substituted for H here, so we get lambda t dot lambda s dot SBT. You'll note that at this point, neither of these are quite complete lists, because I haven't done the tail step yet. I can't do the outermost application yet, because I still need to do this inner application. So this C will be applied to lambda t. We'll substitute the t here, so now we have lambda s dot SBC. This can take a Boolean as a selector to give us B or C. Remember that the kinds of lists we're making have an element as a head and then a list as a tail. So, this becomes the tail to our first list. We can now finally do that application and finish it off by substituting lambda t for this whole block. So that slots in right here where there was a lambda t. And now we have lambda s dot SA applied to lambda s dot SBC. Some careful parenthesization there to make sure that this whole list is inside of that one. Normally, with a list in a language like Racket, you would end with nil here. I've just used C to keep this example a bit simpler. Now, building a list is a bit pointless if you're not actually going to use the list a bit. So, let's use our definition of head and apply it to that list we made before. Now, in AOR, we're going to go leftmost innermost, so in fact, we're going to have to expand head before we can do that whole expansion we already did with cons A, cons B, C. Head is lambda L dot L true. Remember, we can just use true as our head selector. That was why we designed the selectors how we did. True expands to lambda x dot lambda y dot x. There's nothing more we can expand on the left because there's no application that can be done. So now we can expand the right. It's going to go slightly off screen, my apologies for that, but once it's turned into the actual list we're familiar with, then it will fit. So we already went through this expansion and it turns into lambda s dot SA, lambda s dot SBC. Now, we wanted the head of this list, which should be A. So the question is, does this head function actually get the head of a list? Well, we're going to apply this list to lambda L, which is the list, in the head function, and you'll note that it becomes the function in this application. That's because the way lists work is that they are a lambda over a selector, so you have to call the list itself as a function with the selector as an argument. All of the work we've done up to this point is basically just to get the list to the correct side of an application with this lambda L dot L, then true. So this whole block gets substituted for L here. So now this block is this green block here, this pink block is this pink block here, and we have the list applied to true, bearing in mind that the list is lambda s.sa, lambda s.sbc, and true is lambda x.lambda y.x. Now we can do this application, so the selector will come in here. It's currently named S11. Now we have lambda x.lambda y.x, which is to say true, applied to A, and then applied to the tail of the list, where A, of course, is the head of the list. But remember, all true does is select the first of its two arguments. So if we apply true to A, and then the tail of the list, we'll get A. Well, let's prove that. We'll put A in lambda x here. So x13 is substituted for A. That leaves us with lambda y dot A applied to this, but lambda y dot A doesn't even have a y in its body, so when we substitute this in, it just vanishes, and we end up with A. And indeed, what we asked for was the head of the list ABC, and the head of the list ABC is A. I won't show the same degree of detail with tail, but tail ultimately becomes lambda L dot L false, so false is lambda x dot lambda y dot y, that is, it's a function that chooses its second argument. Same kind of expansion we've seen several times by now. And then we end up with the list itself, which remember is a selector, applied to false. False now stands in for the selector, so now we get false applied to A, and then that whole thing applied to the tail of the list. When we substitute A in for X in false, well, false chooses its second argument, so that A just goes away. Now we apply the tail of the list to the identity function that's left out of false, and we simply get the tail of the list. This is a bit less satisfying than just getting A, like we did before, because the tail of the list is still this complicated data structure. But remember, all a list is a selector that selects its head or its tail, and the tail of our original list is the list BC.